Good morning, and welcome to today's webinar, Land and Sea Applications Using SAR. This is the second webinar in the SAR series, and hopefully you were able to watch the first webinar, The Applications and Benefits of Synthetic Aperture Radar. If you didn't, we'll include a link to the recording in the follow-up email that we'll be sending out to you. We have over 1,200 people signed up for this webinar from around the world, so that just shows the great interest in this topic. So we really appreciate everyone taking the time to join us today. For those of you who are new to Harris Geospatial Solutions, just a bit of a highlight. We're the leading provider in software products that extract meaningful information from all types of remotely sensed data. And we've built a reputation as a leader in the hyperspectral analysis space, and our NV product focuses on working with hyperspectral and multispectral and SAR data. I'm Amanda O'Connor. I'm a graduate of the University of Colorado and have a background in hyperspectral remote sensing. Our presenters today are Sarah Black and Megan Gallagher. Megan recently graduated from Boise State University, and she has a master's degree in geophysics with a focus in remote sensing. So, Megan, welcome to today's webinar.
Thank you, Amanda.
Sarah has a PhD in geology from the University of Colorado and is our resident volcanologist and planetary scientist. So again, welcome, Sarah.
Thank you.
Just a couple of housekeeping items before we get started. We've muted the phone lines for all the attendees, so if you have any questions at any point during the webinar, feel free to enter them into the questions chat box, and we'll try to answer as many as we can at the end of the presentation. We'll also be conducting a few simple and interactive poll questions throughout the webinar, and we invite you to take part in each of them. We are recording this webinar, and we'll have it up on our website, harrisgeospatial.com, in the next couple of days. We'll also email you a link to the recording, as well as a slide deck and some other helpful resources, which you are welcome to share with your colleagues. So just kind of an overview of what we're doing today. We've already gone through our introductions. We'll start off with a background on SAR data. Megan's going to show some ocean applications, and then Sarah's also going to show some land applications with surface deformation, and Megan will also show some burn area analysis. So that's what we're going to be walking through today. And from what I've seen from yesterday's Asia Pacific webinar, this is some really fantastic information. I'm pretty excited that we're able to share it again. So now we'll go to our poll question 1. What has held you back from using SAR data? And if you do use it, what is the most trying aspect of using SAR data? So you can select all that apply, and that is the complexity, processing, data availability, storage, or cost of SAR data. So please click now, and you'll have a few seconds, and I'll read out the answers when we get there. Give you a few more seconds. And it looks like the complexity and processing rank is the highest reason for why people have not used SAR data. And those are very common answers to what we hear from other people. So we appreciate you answering those questions for us. So I just wanted to give you a quick overview of the Harris Geospatial software portfolio that relates to today's webinar. We do offer end-to-end geospatial solutions from data collection to dissemination to software and technology to custom solutions to help our customers solve hard problems and make better decisions. We built our reputation with the NV and IDL software products. IDL is the interactive data language. It's a programming language aimed at scientists and engineers who want to be able to read, analyze, and display large quantities of complex data. Our flagship software is NV. NV is built in the IDL programming language and is an image processing suite where you can extract useful information from your data and imagery. It's easy to use and has very many powerful scientific and analytic capabilities. Obviously, we'll be focused on SARscape during this webinar. It's a module built within NV, so SARscape runs with NV. It's really the world's leading analytics product for SAR data. And lastly, our geospatial services framework is a big component of our overall strategy. We've been seeing more and more interest in deploying analytics within the enterprise or cloud environments, and GSF is our way of enabling you to deploy NV, IDL, and SARscape in a cloud environment and receive rapid and important results. So we'll talk a little bit about SARscape. SARscape is developed by SARmap in Switzerland. This is a group full of SAR experts. We work very closely with them to build tools to understand the SAR community and find solutions that are going to best help people solve problems with SAR data. As far as SARscape is concerned, we really see SARscape as an integrated software platform, and its real benefit is that it's scalable as scalable as such as you can use it for operational processing of your SAR data. The other benefit of using SARscape are the ways in which it exposes SAR analytics. Here you see SARscape running within the NV interface. We have pre-built workflows that take you step by step. It exposes all the parameters and gives you easy online help to work through these workflows, and there are many pre-built ones within SARscape, and we'll talk through some of those today. And then in the most recent release, we've enabled all the SAR analytics to be available as tasks, which means you can use them within the NV modeler. And that is really useful for those of you who prefer not to program, myself included, and want to build your own processing chains in a drag and drop environment. So it's very similar to the Esri modeler or the Esri geoprocessing tools if you're familiar with those. And next you'll see ArcGIS. Hoping we have a lot of ArcGIS users online today. For those of you who are interested in SAR as well, we are able to expose all of the SAR analytics within ArcGIS Pro. And lastly, we can take the SAR analytics from the desktop through the enterprise or cloud environments. We support all the major cloud providers as well as people's in-house cloud or server environments. On the screen now, you'll see that we show the GSF dashboard example exposing SAR analytics within a web interface. I think the key message here is that there are many ways to access SAR tools within multiple environments and get answers quickly and easily in the environments that we provide. So now we'll go to our next poll question. How would you prefer to get results or answers from SAR data? Would you like to have guided workflows help you find answers? Would you like to get answers delivered to you, so like a layer that you would get from us? Would you like to do it yourself or other? Let me give you a few seconds to click into that. And looks like most people are guided workflows and do it yourself, and that is pretty much what I expected, and that's how many others have responded to these types of questions as well, and customers that I've talked to. So we'll be addressing actually both of those ways of approaching SAR data in this webinar. So I think you'll get some good information. Okay, and now I am going to turn things over to our first presenter, Sarah. So welcome, Sarah, again, and look forward to hearing you discuss basically some first principles of SAR data.
All right, thanks, Amanda. So before we get started today, let's go over a few key ideas from last month's webinar. If you haven't seen last month's webinar, I definitely recommend you go back and watch that. It's available on the Harris Geospatial website. We have a recording. So if you remember from last time, optical and SAR sensors work differently, and this has an effect on how the data can be collected. Optical imaging sensors are passive, which means they measure sunlight that has been reflected off the Earth. However, if there's interference, such as clouds, as we see in the example here on the left, that reflected light can be blocked, which prevents data collection within an area. So in our example on the left here, you have this optical image that's full of clouds. This is very common in many areas on the Earth, particularly in the tropics, or if you're trying to work in areas where there are storms. And that makes it really tough to get the data that you need. SAR, however, is an active sensor, which means it provides its own illumination in the form of an emitted microwave. And this microwave can travel through cloud cover, and the reflected signal is transmitted through cloud cover as well. And this means that SAR is capable of imaging a scene day or night, and it's not sensitive to cloud cover. So in the example on the bottom right, we have a SAR scene, and you can see there are no clouds in that image anywhere. From the radar backscatter, we get two different types of information. We get both the amplitude and the phase of the response. The amplitude is the magnitude of the signal, which shows how much or how intense the response was when the radar signal hit the ground. And this can change based on physical and chemical characteristics of the object that the signal interacted with. The phase is the position of the wave within the time period of its cycle. So today we'll look at different types of analyses that you can do using both the amplitude and the phase. When you're preparing for your analysis, there are a couple things you need to do first. So first, of course, you have to find and download your data. And as we discussed in the previous webinar, there are many different SAR satellites with different sensing bands, spatial resolutions, and revisit times. So you'll need to make sure you take some time to decide what data set is most appropriate for what you're trying to do. For our examples today, we're using a mixture of Sentinel-1, RadarSat-2, and ENVISAT data. For most SAR analyses, you will also need a DEM or digital elevation model of your area of interest. Today we're using ASTER and GTOPO30 DEMs, which are freely available from the USGS Earth Explorer website. If you have the newest version of SARscape, you will also need to set your data format specific preferences, which you can see here on the right. This automatically populates the optimal settings for whichever data format you select when you're running various workflows and tools. You can still change these settings if you want, but this gives you a very good starting point that you can work from. Also, it's a really good idea to get yourself in the habit of checking your settings anytime you open ENVI and start working to make sure that they're correct. In the previous webinar, we went over a few general uses for SAR data like DEM generation, flood mapping, and activity monitoring. Today, we'll go into more detail and show you how to run your own workflows doing things like bird area analysis, identifying oil spills and ships, and of course, my personal favorite, volcano interferometry. So there are a lot of different ways that SARs can be used in the ocean. Today, we're only touching on oil spills and ship detection for ocean applications. But SAR is currently used for many different applications within the ocean. Some of the other things you can do with SAR in the ocean is things like identifying waves, identifying shallow bathymetry, looking for wind effects on the surface of the water, and identifying other surface coverings such as plant matter. So let's start with our first example of the day. We'll look at some ship detection using SAR data. This type of analysis can be used across a wide range of applications, things like tracking shipping lanes or monitoring protected areas and making sure that there aren't people taking ships in there that shouldn't be. So we can detect ships using SAR because of a difference in how the radar signal is returned to the sensor. If you remember from our previous webinar, the radar signal can experience diffuse, specular, or double bounce backscatter, and there are examples of each of these shown on the bottom left. The type of backscatter you get depends on the type of surface the radar signal interacts with. Things like smooth water bodies, such as the ocean, produce specular reflections, where the majority of the radar signal is reflected away from the satellite. And this creates dark pixels in your SAR scene, like you can see in the example here on the right. Ships in the water produce a double bounce, which returns most of the radar signal to the satellite and results in bright pixels in your SAR scene. So you have your radar signal coming in and having specular reflection off the water initially, and then it bounces again off of the ship itself and returns to the radar signal. For our ship detection workflow, we'll use Sentinel-1 GRD, or ground range detected data. GRD data is already multi-looked and converted to ground range. It just needs to be geocoded to be ready for your analysis. GRD data is a very useful format if you're interested in working with only the intensity information, since for GRD data, the phase information is stripped out to make the files smaller and faster to work with. One important thing to note if you're working with GRD data is the spatial resolution. So since GRD data comes already multi-looked, you lose some control over what spatial resolution you can work with. For today, we're using Sentinel-1 Interferometric Wide Swath, or IW, high resolution data. And this is about 20 meters per pixel after its processing. There's also full resolution scenes, which are about 9 meters per pixel, and medium resolution, which are about 90 meters per pixel, or 90. So your first step in most processes is to import your data. Here you can see the Import Sentinel-1 tool in the SARscape toolbox. And this works for both GRD and other data formats like SLC or single look complex, which we'll show you some more later. Under the Parameters tab, there are options to select different polarizations. You can mosaic tracks that were acquired sequentially within the same orbit, and you can make a multi-looked power file. Your other preparation step is to get your DEM into a SARscape compatible format. And this is a very quick step that only takes a minute or two, and you need to do anytime you're bringing in your own DEM from somewhere else, or if you're downloading it from online. To begin, if you're using more than one DEM tile, you'll need to mosaic them together using the Seamless Mosaic tool in the NV Toolbox. In the Export tab, be sure to set your output format to TIFF. Once you have your DEM mosaicked, or if you don't need to mosaic it at all, you'll then need to import the TIFF using SARscape's Import Generic TIFF tool. And this creates the necessary .sml file to make your DEM compatible with all the SARscape tools. So for those of you who are familiar with NV file formats, the .sml file is the SARscape equivalent of NV's .hdr or header file. And this contains all the necessary metadata to read the file properly. And once you do this with your DEM, you don't have to do it again. It will now be compatible with SARscape tools in perpetuity. Before you run the Import Generic TIFF tool, make sure you set your data units to DEM in the Parameters tab so it can be recognized as a DEM. So now that you have your SARscape compatible DEM, it's time to create your landmask. So we'll do this by using the Band Threshold to ROI, or Region of Interest tool. When you open this tool, the histogram for your DEM is displayed. You can see it here in the middle of your screen. You'll set your minimum value to 1 and leave your maximum value as is. After you click OK, you'll save the resulting ROI, or Region of Interest, as a shapefile. You'll see that here on the right. So all of the land is in red and all of the ocean is in black. So now you have your landmask. And make sure you check this before moving on and fix any gaps that there may be or anywhere that you're not happy with the output. There are also coastline shapefiles available all over the world that are available for you to use if you prefer to use those instead of the DEM. So now that you have your landmask created and you have your data, you're ready to run the SARscape shift detection workflow. So you'll input your SAR scene into the input files and input your landmask in the Optional Files tab. Under the Parameters tab, you may adjust the various window and buffer sizes to tweak your output. And this workflow doesn't take long to run, it's only a minute or two, so don't be afraid to experiment with these and see how they affect your outputs. You'll need to fiddle with them a little bit to get something that you're happy with. What you use for these inputs is going to depend on what size of ship you're looking for. So once you've played around with it and adjusted the values to your liking, you're ready to run the workflow for the final time and get your final output. In our example here, we have our original SAR data on the left, and then on the right, all the ships are highlighted using red crosses, and our output on the right. And this output is as a shapefile, and you can save it as a shapefile and use it in any other program you'd like that you can manipulate shapefiles. So NV, ArcGIS, anything. In addition to simply detecting ships in your SAR scene, you may also want to use the AIS, or Automatic Identification Systems data to compare your results. AIS beacons are required to be transmitting on large ships at all times. However, sometimes ships turn these signals off or alter them to report a different location if they're doing something or they're going somewhere that they don't want people to know about. The combination of SAR ship detection and AIS tracking through the SAR AIS classification tool can identify which ships were identified in both the SAR scene and the AIS data, and which ships were detected in the SAR scene but not the AIS data, indicating these potentially unsavory activities that you may want to look for. So here our friends at SARmap have run the SAR AIS classification on a RadarSat-2 scene over Greenland. The yellow crosses mark ships that were detected in the SAR data, while the purple lines show the AIS data of ship tracks. The green circles show ships that match in the SAR and AIS, while the red circles indicate ships that were identified in the SAR data but do not match up with any AIS tracks. So ships that may be doing something they're not supposed to be doing that you might want to look into. So we have a very versatile set of tools for ship detection in SARscape, and don't be afraid to go play around with it. They're very simple to use, and you can run them very quickly and see what you get. So now I'll turn it over to Megan, and she's going to show you how to look for some oil spills.
All right. Thank you, Sarah.
So, like Sarah said, now we're going to move into oil spill detection. When we are looking at optical imagery, or even just looking at the picture on the screen in front of you, oil spills can show up as sheens that appear on the surface of water. However, dependent on the weather and surface conditions, it may be impossible to view these sheens with optical imagery, especially in many situations that might cause these oil spills to begin with. SAR data then is great to use as it can see through these weather effects, and oil spills have a very different surface tension than water, making them stand out against the background water response. It should be noted, however, that some oil spill responses are very similar to calm water bodies, so it is necessary to have an understanding of your oil spill and area of interest. We are going to be using two examples for viewing oil spills. The first is the Anor oil spill. This oil spill happened in early 2017 and occurred from the collision of two oil tankers outside of the Kamarajar port near Chennai in India. An oil slick was seen surrounding these two vessels, and the shore was later confirmed to have tar balls and oil residue. This oil slick also affected the local wildlife. We will be using Sentinel-1 scenes for this dataset. The second example is an oil slick outside of Gotland Island, Sweden. The cause of this oil spill is unknown, but it is readily apparent in the patterns that we will see soon. NVSAT imagery is used for this dataset. For ship detection, we started with the GRD, downloaded directly from the web service of your choice. But for this example, we're going to go through steps for pre-processing SLC, or single look complex data. This data has both the phase and intensity, as opposed to GRD, which only has intensity. But the SLC has also been focused and geo-referenced using the satellite information. When using SLC data, you have more choice on your output resolutions and can use the phase information for more complicated analysis. We're going to go through the same workflow that we did in the previous webinar, so it may be familiar to those of you that saw that one. So here's an example of the workflow for all of the pre-processing steps of the SLC data shown in the NV modeler. This workflow goes through each step automatically to return the output parameters that can either be saved, shown on your screen, or moved into further analysis. The modeler works wonderfully for programs that need to be run multiple times, and you can set up loops and iterations to go through multiple scenes and get all of the final outputs. I am very much a big fan of the modeler. So we're going to go over the pre-processing steps with the Anor oil spill example. We already went over importation, which uses the same tools, be it GRD or SLC, so we can move right into the next step. Multi-looking is used to remove speckle or noise that is seen in SAR scenes by averaging neighboring pixels. This does reduce the spatial resolution, but decreases the noise that occurs in the scene. The output of this is called a .pwr file or a power image. The next step, when you're using only one scene, is filtering. If you're using more than one scene, you will co-register them first, making sure that they all overlap evenly and can be used in tandem. Filtering is used to reduce speckle and pull out the background information that might be hidden by that noise. And the filtering method you use will depend on if you have a single scene or multiple. De Grande filtering is used when you have 3 or more images, and it uses both space and time to filter all of the images and remove atmospheric effects. There are many different filtering methods that can be used. In this case, we're using a single image filter to reduce the noise. And if you look at the images on the screen, the one on the left is only multi-look, and the one on the right has been filtered. And we're really drawing out some of that background information that was hidden before. The last step in pre-processing SAR data is to geocode it. After the SAR data is multi-looked and filtered, it is still in ground range geometry and needs to be projected to a meaningful coordinate system. Previously, it looked as if the port was on the western side of India, and now it is correctly located. With the pre-processing steps finished, we're going to move into polarization, which is very important when looking at water bodies of SAR and for more advanced techniques. Polarization is the direction of the wave that is projected from the radar, and then the direction of the wave that is returned after it is bounced off an object. By that, we mean that if a wave leaves the satellite and it is oscillating up and down or vertically, then hits an object on the ground, and returns with the beam oscillating vertically again, then you have VV, or vertical-vertical polarization. When the polarization is VV or HH, which is horizontal-horizontal, it is called copolarized. And when it is VH or HV, vertical-horizontal and horizontal-vertical, it is cross-polarized. Different polarizations react differently to ground surface characteristics. So the more polarizations that you have, the more in-depth an analysis you can go. For example, we have been viewing the VV scenes over the oil spill in Anor for a very important reason, and that reason is they're not even viewable in the VH imagery. Understanding the effects of polarization is dependent on the surface you're viewing. As you can see, VV over water is more sensitive to surface conditions, and when you're looking over land masses, VV is able to pierce further through vegetation than VH. HH is used widely for looking at sea ice as well. So it does just depend on what you're looking at to choose the proper polarizations that'll work best for you. Now, on to our last example of a small portion of the Gotland, Sweden oil spill. The image has been stretched, so it's easier to view this oil track. So with the oil spill and how different it is from background water, you were able to create classification images of them. In this case, a simple unsupervised classification was run in Envy, and we're able to get the entirety of the oil spill classified, with which we can do later analysis, such as tracking of change over time, or understanding of the area covered by the oil spill, and we can get useful units of measurement from it, such as total area. With that, we're going to move into land applications. Now, I would love to list all of the SAR land applications, but in all honesty, that would take up the rest of our time. So here are just a few of the many uses of SAR. On the screen in front of you, we have images that are showing snow mapping, activity monitoring, flood mapping, soil moisture, and land surface subsidence. When you think on a topic and wonder if you can use SAR for land applications, just remember what it's sensitive to. Surface roughness, moisture, water form, be it liquid or solid, slope, motion, and chemical and physical properties of structures. If what you're interested in is somehow related to any of these topics, which it probably is, you can test out what SAR will give you as a result. The first land application that we're going to walk through is using SAR data to find fire extent, an area of burn scars. As we talked about in the beginning of this webinar, one of the best practicalities of SAR is that it can view the surface even through smoke and clouds. For this example, we're going to look at the Camp Fire. This fire started November 8th in Butte County, California, in the United States of America. This fire lasted for 17 days and is the deadliest and most destructive fire that has ever occurred in California and the 6th deadliest in the United States. It has also now been classified as the world's costliest national disaster of 2018. The smoke from this fire covered most of the Central Valley of California and was even visible on the East Coast, and caused areas around the Bay Area to close down schools and businesses because of the air pollution. With this fire, and many others that have occurred internationally, we found it more and more difficult to get up-to-date, immediate imagery that can aid in outlining the extent and effect of these fires. As such, using SAR data is becoming more and more necessary for the best understanding of what is occurring on the ground surface level. For this methodology, you're going to need SAR imagery over multiple days with pre- and post-fire imagery. Excuse me. In fact, the more imagery you have, the more cohesive your results. I will get more into that when we talk about one method for this analysis. The next information you're going to need is a DEM. Previously, as we were focused on the water side of SAR, a DEM wasn't technically necessary, though you probably should have one anyway. However, as we move into land surface analysis, DEMs are essential. Lastly, for data, a shapefile around the campfire was downloaded from the CAL FIRE website for total extent. The processing for this method is the importation of SAR SLC data, and then using the workflow for coherent change detection. To go into a bit further analysis on the necessity of DEMs, when using SAR, there are multiple geometric effects that can occur specifically in terrains with large amounts of vertical change. Mountain ranges and valleys can have these effects dependent upon both their geometry and the viewing angle geometry of the satellite or plane that is being used. The first example shown is called foreshortening. This occurs when the angle of the satellite makes it seem as if areas of terrain are closer to others than they physically are when the waves return to the satellite. So as you can see on the image to the far left, B looks as if it's much closer to A than it should be. The second example is layover, which is an extreme version of foreshortening, where the geometry combination of satellite and terrain makes it seem that points further away are returned to the satellite first, thus making them seem closer. So if we look at the middle image, B is now moved in front of A. Lastly, we have shadowing, where you're unable to pick up specific points as they are hidden by the terrain. A high-resolution DEM is able to correct for foreshortening errors. However, layover and shadowing errors cannot be corrected and can only be calculated. The SARscape workflows have the ability to create automatic masks that show areas that are affected by layover and shadowing. And these masks can be used to ensure that the data that you're looking at is correct and not an artifact of geometric effects. We had a lot of interest in the past webinar about using SAR in mountainous regions, and it can absolutely be done. You just need to view the possible effects of layover and shadowing to make sure that the area you're interested in is viewable and processable using your satellite system of choice. Now we're going to talk about coherence change detection, or CCD. We spoke previously about phase and amplitude. CCD uses changes in the phase and amplitude to pinpoint surface changes from SAR data. CCD uses the changes that occur over multiple images to see where there's coherence or similarities. In this slide, we're looking at the intensity alone, which is the amplitude squared, over the campfire. You can see areas where there are major changes from the SAR response pre and co-fire. Using the intensity, we can see these changes where some areas are brighter, where the previous vegetation had scattered the SAR waves, has now been removed, and the waves are bouncing off of bare soil or low shrubs. When we take a look at the phase and intensity change, however, we have a much clearer view on the areas of large change between the pre and co-fire imagery. Dark areas are where coherence is low, and in this case, even from this pair of images, we can see how well these areas of low coherence line up with the fire boundary. The image on the left is coherence from a pair of images from before the fire. We do see low coherence in the mountains and even where the fire is going to occur, and this is caused by thick vegetation. However, in comparison to the coherence from during the fire, there are obvious changes that show the removal of surface structures. Finally, we're able to see the difference between the two coherence images and pinpoint those areas that had large change between the pre and co, as seen in the black. Now let's go into how you can get these results and what you can do with them. There are multiple CCD workflows that are available in NV SARscape, and most of them use a pair of images. And depending on which one you choose, you'll get a different colored output. In this example, we are using the CCD timeline, which uses more than two images. The reason this is chosen are areas with vegetation have low coherence seen because of the scattering. So to get higher accuracy results, we want to have more images that are available for analysis. The workflows that are available in SARscape go through the analysis step by step and allow you to add inputs and change specific parameters. One of the great things about these workflows is you can make importation and sample selection in the workflow itself. The first step in CCD timeline is a possibility to import the data if it hasn't been already. The second is to create a smaller region from our SAR scene, which is very useful for processing if you're only interested in a smaller area, as opposed to a large encompassing SAR image. This also makes the processing much faster. With the first two pre-steps done, we can get into the actual CCD processing. Multi-temporal coherence is the first step, and based upon your grid size and sensor type, the parameters will be automatically updated for what works best for your situation. All of these parameters can be changed if you want to test more advanced techniques, but the base parameters work fantastically for all the processing. Multi-temporal coherence step calculates the similarity between the pairs of SAR imagery using interferometry, which we'll be getting into more very soon. The similarities and differences between the phase and amplitude response of the pairs shown show how coherent they are. Things that will affect this coherence are either noise between the two scenes or temporal change, which is what we are interested in. After that step, we move into geocoding. This step is what transforms the SAR data from its slant range geometry to its geocoded frame of reference, such as we just did with the oil spill. The last step is the color composite, creates a colored image of the coherence. There are multiple ways to view this imagery, as well as choices you can make to have the best fit for the output that you need. And here are the results. We're using 3 images to generate this coherence change detection, 1 from before the fire and 2 during. The bright blue-green color in the middle shows the areas that had major change during the first period of the fire, up to the end of November 9th. The ring of red around that shows the major change between November 9th and November 21st. We can see how these burn areas clearly change over time. And if you look at the bottom left of the screen as well, you can see that the CCD was showing the changes in the agricultural fields just south of the campfire. These outputs can be used for multiple end-term results. Classification is possible using the coherence changes to get areas of high to low change. If previous in situ information is available, or even an understanding of the vegetation of the region, we're able to calculate biomass change from before and after the fire's occurrence. Lastly, these SAR images can be used in tandem with optical imagery to get in-depth analysis using data fusion for change detection. And with that, we're going to go back to Sarah with our last topic of the morning, and what I know to be her personal favorite. Thanks, Megan. Yes, I do love volcanoes. So let's get into some interferogram generation. For this example, we'll be walking through our DInSAR, or Differential Interferometric SAR workflow. And we'll be creating an interferogram and displacement map from the new vent development on the Kilauea volcano in Hawaii in the United States that occurred in May 2018. This eruption destroyed 700 homes and caused over $800 million in damage. So it was a very heavily monitored eruption. For this analysis, we'll use Sentinel-1 scenes from April 20th and May 2nd, 2018. Interferometric SAR uses the change in phase from one time to another to measure the displacement of the land. So in the example in the bottom left here, we have the movement on a fault, which is lowering the land on the right-hand side. And this means the radar signal has to travel slightly further to reach the ground, and that means it returns to the satellite at a different point in its cycle. In interferometry, we use this change in phase to identify land deformation. So common examples for interferometric analysis are using earthquakes and volcanoes, but you can use interferometry for all kinds of surface deformation. DInSAR can detect displacements of a few millimeters, but it's really best for larger displacements because it doesn't model atmospheric effects on the data. This really requires something like external models or an SBAS, or small baseline subset analysis. And we may get into more complex interferometric analyses like SBAS in our third webinar, but for today we'll be working with 1 pair of SAR scenes and creating 1 interferogram. There are a few very important rules that you have to keep in mind when you're preparing for an interferometric analysis. First and foremost, you must make sure not to mix your data. So this means not only satellites, but also acquisition geometries and relative orbits. So before you go gathering your data for analysis, you'll need to figure out which acquisition geometry and relative orbit you want to work with. If you're working with the Sentinel-1 data, you can do this right on the Copernicus website. So when you're searching for your data, you'll click on the View Data Products icon for a scene you're interested in using, and that's highlighted in the little red box here. And this will bring up the details regarding that scene. If you scroll down in that window, you can expand the Product tab and find all the information you need, like path direction, which is the viewing geometry, or ascending or descending, and also the relative orbit. You can also find the polarizations that are available, which is also important because you only want to use copolarized data, which means VV or HH data for interferometry. One other thing to keep in mind is that low coherence makes interferometry difficult. Things like heavily vegetated areas are particularly problematic with low coherence when using C or X-band data like Sentinel-1 and TerraSAR-X. Other problems can be things like landslides, where you have a lot of change between time 1 and time 2. Once you know what acquisition geometry, relative orbits, and scenes you want to use, I would highly recommend downloading them using the SARscape Auto Download tool. I'm a huge, huge fan of this thing. It's fabulous. It eliminates the need for manual intervention when downloading multiple scenes. So rather than sitting there on a website and clicking download over and over, you just enter your parameters like date, location, relative orbit, and viewing geometry, and the download tool does the rest for you automatically. And this is also extremely helpful if you're getting into more complex interferometric analyses like SBAS, where you need lots and lots and lots of scenes. So once you have your 2 SAR scenes and a DEM, you're ready to get started. Having an ROI shapefile also helps by cutting down on the processing time, but it's not really necessary to run the analysis. However, I would highly recommend it if you can. Before you go starting the workflow, you're going to make sure to go through all your settings for each step and each tab before clicking next and starting the workflow, especially setting your output directory. Trust me, you will only make that mistake once. So we begin by setting our input files and our area of interest. For the DEM, you need to remember to make sure that it has that .sml file so it's SARscape compatible. And this is done through that SARscape import generic TIFF tool we discussed earlier. Under the Parameters tab, if you have already imported and subset your data, you can skip both of those steps here by setting both skip import and skip sample selection to true. I highly recommend you import and subset your data before running any workflow, since those steps can take a little while and you only want to do it once. That way you can save it somewhere and access it at any time for any project. It's a great habit to get into to save yourself some time in the future. So if you've remembered to set your data format specific preferences before starting, all of the inputs in the other steps should have automatically populated to be most appropriate for your data format. However, you still need to step through and check everything, and there are a few changes that you may need to make. In the interferogram generation step, you can set your grid size to your desired resolution. And if you don't need a lot of detail, making this value larger is going to make your processing run faster. The adaptive filter and coherence steps should be all ready to work with your data set. So unless you have something specific that you want to tweak in the parameters menus, which are available in the drop-down at the top, you can leave this setting alone. In the phase unwrapping inputs, you'll select the Delaunay MCF, or minimum cost flow method. And you can also increase your coherence threshold if you like, but 0.3 is a good place to start, and you should never go below that. If you go below 0.3, you're getting into too low of coherence and your output products won't be any good. The unwrapping decomposition level may also be adjusted, but 1 is a good starting point. You'll use 0 if your interferogram fringes or those bullseye rings are very narrow. And this is common for earthquake analysis. But 1 is an acceptable place to start. A lower decomposition level makes the processing take longer, but it's needed for more detailed analysis. On the other end of that spectrum, you'd use a decomposition level of 2 if you're working in a large area that has infrequent interferometric fringes and doesn't need a high level of detail. For the GCP selection step, first you'll leave these inputs blank for now, unless you already have a good ground control point file or GCP file for your region. When the workflow is running and it gets to this step, if you've left it blank, it will stop, and you can do this then. So we'll come back to this step in a moment. Your refinement and reflattening inputs don't need any adjusting unless you have something specific you want to tweak, so you can leave these as is. And under the phase to displacement step, you should make sure the vertical displacement option is set to false. It's very important to remember that with single pair DInSAR, all the displacement calculations are relative to the satellite line of sight, so they're always less than the real vertical component. If you want to create a true vertical displacement map, you'll need to use a different workflow, the dual pair differential interferometry workflow. To create a vertical displacement map, 2 different viewing geometries are needed to resolve the vertical motion. This means the dual pair differential interferometry workflow requires 4 SAR scenes, 1 ascending track pair and 1 descending track pair. For today, we'll only be covering the single pair DInSAR workflow, but if you're familiar with interferometry, and you should be after today, so the dual pair differential interferometry workflow is relatively easy to navigate. So don't be afraid to test it out and apply these concepts that we've gone over today on your own. So to finish up our DInSAR analysis preparation, for the output, you'll set your desired output directory and root name. And the final output of the DInSAR workflow is your displacement map. So if you want that intermediate interferogram step, which is that nice, pretty classic bullseye ring map that people really like to look at, you need to make sure to uncheck delete temporary files. The interferogram is an intermediate step, and it actually ends up in your temp folder. So if you don't uncheck this box, it will be deleted if you don't uncheck it. Once you've run through all these inputs, you're finally ready to click Next and start the workflow. But remember, there was that ground control point step that we skipped over before. If you input a pre-existing GCP file, the workflow will run from beginning to end with no interruption. But if you left your GCP input blank, the workflow will pause when it gets to this step. So now you'll click on the binoculars button to bring up the Generate Ground Control Points tool. This will automatically populate the input, DEM, and reference files using the files that have already been created in the previous steps. All you have to do here is click Next. This will bring up the GCP generation tool in the NV viewer, which you can see here in the bottom right. When selecting your GCPs, you should create at least 25 points, although more does not hurt. And these points should be located towards the outside of your scene, as far away from the area of displacement as you can get. When you select a GCP, you're saying that point has not moved at all. So it's important to stay far away from any potential displacement. All of the reported displacement in your final outputs is relative to the GCPs you select. So placing these is a very critical step. Also keep in mind that the scene you're working on at this point is not geocoded, so you need to take a minute to orient yourself before you create your points, so that way you know you're putting them in the right place. In this case here, the Big Island of Hawaii is flipped vertically, so the south coast is at the top of the image. For this data here, you can see the bullseye type fringes around the area of displacement in the red box in the upper right corner. So we need to make sure to avoid that region when selecting our points. GCP points are also used to get rid of any phase ramp that remains from incidence angle variations as you move across the scene. So the points you select should span your scene vertically and horizontally as much as possible, while you're also avoiding any fringes you can see that may be attributable to topography or atmospheric effects, like the summit region of the Mauna Kea volcano shown here in the yellow box. Once you've created your points, make sure to check your output directory and file name in the Export tab before you click Finish. Change it if needed, and then click Finish to save your GCPs and continue on with the workflow. And once you make this file and you save it, if you need to run this again with the same data, you can just pull that GCP file in the original input window. So you don't have to do this every time. So several products are created from this workflow, as you can see here. In addition to the classic interferogram shown in the middle, you also create a coherence map on the left and a displacement map on the right. So let's zoom in on the areas highlighted in the red boxes so you can really see and appreciate the gorgeous detail a little better. The speckled areas in the interferogram on the left are areas of low coherence, which is, again, due to things like highly vegetated areas. And it's important to remember that your displacement maps from DInSAR processing, like the one showing here on the right, are showing displacement along the satellite's line of sight. So these are not true vertical components. Here, our positive displacements are either vertical or to the west, since the satellite line of sight is looking roughly east. The negative motion is either downward or to the east. So again, this is not a vertical displacement map. This is a satellite line of sight map. So in today's webinar, we've included all the information you need to get started with these workflows and more. And now you're ready to get some data and start playing around. So don't be afraid to try things out, work back through the workflows we've shown you here today. In many of these cases, we've told you the exact data we use, so the satellites and the dates, and you can go get it and walk through step by step exactly what we've done here and compare your outputs and see how it goes. And we're always here if you have questions. Now I'll turn it back over to Amanda. We have one more poll question for you.
Awesome. Yeah, so we have our last poll question. Thank you so much, Sarah. Thank you, Megan. For the next SAR webinar, what areas would you like to see expanded upon? Agricultural monitoring, temporal land surface deformation, so SBAS or persistent scatters, polarimetry, or maritime and oceanic needs like sea ice or surface wave effects. So now a few minutes to vote. And again, agricultural monitoring is in the lead, and I know Megan's very excited about that. She's doing her happy dance right now. And also temporal and land surface deformation SBAS. So both you've made Megan and Sarah both very happy this morning. All righty. So just wanted to cover a couple of upcoming events in the next couple of weeks. We've got ILMF and ASPRS that are happening in Denver, Colorado. We'll be at booth 213, and you can come talk about SAR or LiDAR or imagery with any one of our representatives. All three of us will be there, so if you're around, please come say hello. We are also still in the planning mode for our third webinar in the SAR webinar series, which will take place on April 3rd, and as you just answered, it will likely cover some agricultural monitoring. So, and that's fast, okay. And we'll send out email invitations to everyone who registered in the first and second webinars. So, let's see, do I have anything else on this? So I wanted to thank Sarah and Megan for a very informative presentation. As a hyperspectral scientist, I've thought of a ton of new questions and kind of kicking myself for not learning more about SAR sooner, because there are many things I could have addressed. You know, it's like learning a new language. Like you're able to ask new things out of the data that's available to us, and you know, the Sentinel data that's freely available, the other instruments, SAR instruments that are available, let us, you know, explore our data, explore our world with a lot more information, be able to see through clouds. So the value of SAR is just absolutely apparent to me, and the value that SARscape brings to being able to work with this data quickly and easily is just tremendous. So thank you both for your time, and I'm very excited that we have a chance to go through some of the questions that you guys have sent us. So thank you very much. So where would you guys like to start? We've got a couple here. Actually, you know, we'll start with Sarah. I think this one is for her because she's so excited about SBAS. When should I use SBAS versus persistent scatterers?
All right. So SBAS and persistent scatterers, or PS, do similar things, and it's looking like we'll probably cover these topics in the third webinar, so we can go into some more detail, which I'm very excited about. They do similar things, but in slightly different ways. So persistent scatterers is really great for things like urban environments where you have buildings, which are your persistent scatterers, and you're tracking the movement of specific points through time. SBAS is looking at more kind of diffuse across a large area motion, and you end up getting back a raster with pixel values of motion. And yeah, we'll get into more detail on this in the third webinar.
Okay, sounds good. And then what about SAR for agriculture? Since people seem interested, I think it's worthwhile to make a little bit of a comment there about how it can be used in a general sense.
Definitely. So SAR for agriculture is a very big thing at the moment, because a lot of times when you're trying to track agriculture or track growth, change, classify between fields, you're growing in areas where they get a lot of rain and a lot of clouds, because that's what you need to grow a lot of these crops. And so using SAR for ag and the ability to see through these clouds, and sometimes the rain does add a bit of noise depending on what's occurring in the atmosphere, you're able to get much higher temporal resolution in tracking. And so the thing about using SAR for agriculture is that it can absolutely be done, and there's many different ways you can look at these different plant characteristics and even soil moisture, but you really do need some in situ data, such as you need to know what kind of crops are growing or what the specific field is, because all of these different characteristics might affect what the SAR satellite sees. So SAR for agriculture is an amazing thing, and I'm really looking forward to see if we can cover it in the next one. But it does need a bit of that background information for when you're looking through this kind of stuff.
Cool, thanks so much, Megan. We've got another question. What can I use CCD for? I think that's also maybe Megan.
Everything. So CCD is a mixture of using the intensity and the phase for looking at changes that occur, or I mean, in this case, coherence, so similarities. And so if you're looking for areas that might have change or to see how similar scenes are, CCD is essential for really understanding what's going on in a scene. For the campfire and for the previous images you saw the last webinar of Burning Man, CCD is really able to pick out all these different kinds of changes, be it in urban areas or rural. And so the thing about CCD is you're just looking for that similarity. Whereas if you're going to interferometry, you're trying to track those changes. So if you want an understanding of a scene, you can use CCD.
Great, thank you so much. So I've got another question. Does SARscape come with NV, or is it a separate product that can be purchased? So you need to have an NV license, and then SARscape is a product that sits on top of NV, so it would need to be purchased. And you can email me if you have further questions on cost in your local region. So we've got time for a few more questions.
So We have some people asking about how the shift detection algorithm works specifically. It's pulling out the differences in backscatter. So it's looking at the average backscatter in your region and getting the sort of the baseline backscatter from the ocean. So finding that dark backscatter value, and then looking for things that stand out from this average, which is where you get your shifts. And so it's pulling out those bright spots that are surrounded by dark. There are also some questions about the AIS data. The AIS data, actually, Harris is a provider of AIS data. So if you're interested in that, we can provide it for a fee, and just contact us at info@harris.com.
Great.
Let's see, we also have a question on the unsupervised algorithm that I used for the oil spill. I just used a very simple ISO data classification. It took maybe 3 seconds to run, and the difference between the background water and the oil was so apparent that it just classified all of it. Now, ENVI does come with many different supervised, unsupervised, machine learning, and even deep learning techniques. So depending on the situation you're looking at, there is most definitely a classification that'll work for you.
We have a question from Antonio asking if GCPs are mandatory for DInSAR displacement workflow. There are actually now, with the new SARscape update, you can run interferometry workflows without GCPs, but it's really not recommended. So you can do it. Technically, they are not mandatory now, but you should create GCPs. It only takes a minute, and it makes your outputs much better because it's giving a baseline zero motion point to work from. So if you don't do those, your outputs aren't going to be as good.
I can also add on to that. You can do InSAR or interferometry without GCPs.
Yeah.
Once again, with those warnings that it will never be as good, but using DInSAR without GCPs is an automatic warning actually pops up that pretty much says, like, don't do this. You can do it, but we really recommend against it.
Yeah. Yeah, they have a little pop-up to warn you.
Yeah.
Like, you sure you want to do that? Yeah. Let's see, Megan, there's a good question for you. Tatiana is wondering if they can make a color composite to feature different types of vegetation.
So when you're looking at that, it's really dependent upon, well, the answer is yes, absolutely. Because if these different kinds of vegetation have different responses, you can do things such as have these different polarizations or different characteristics that really highlight those vegetation differences. Or you can do things like classification to pull them out as well. So depending upon the vegetation and the kind of data you have, absolutely.
Great, thank you. And I just wanted to comment, it looks like Mike has some questions regarding some military applications with ENVI, Jaguar, and SARscape. It's probably a little bit longer conversation, Mike, but absolutely there are certainly military applications in being able to detect different kinds of surface roughness, being able to see through clouds and areas that are kind of persistently overcast, and optical data is not so useful. So we'll be sure to follow up with you and let you know how to get access to SARscape and ENVI and Jaguar. It looks like we are pretty much to the end of our hour. I want to thank everybody for attending and your time. I really appreciate it. And thanks so much to our presenters, Megan and Sarah. You both just rock. We're so happy that we have you guys here.
We're both geologists, so we appreciate that. Thank you.
All right, we're getting funny here. So it is time to stop. So thank you, everybody. I hope you guys have a wonderful day. Please come by and see us at our conferences, and we look forward to seeing you in the third webinar.